Okay, so test review today, and test is on Wednesday of this week. So we finished everything basically, and I wrote out a new review for you, so that's why it's not in your guided notes book. So this is what I'm handing you printed copies of. And let's look at some of these problems that will kind of give you an idea of what you will be expecting for the test. The first one, if 50% of all dogs in St. Lucie County are golden retrievers, what's the probability that you randomly select 5 dogs and none of them are goldens? Now, I don't have my book here with me, but you need your binomial table for this test, and it'll be on the test. And make sure you have that and your formula sheet as we go through this, okay? So this one is actually a binomial problem. Now, I recognize it because it could be either golden or not golden, right? Those are the two choices. So what's the probability of golden, which is the question they're asking us? That would be P. And the probability of golden is 50%, 0.5. 50% of all dogs in St. Lucie County are goldens, right? So we got a probability of 0.5. And then we say, okay, what's the other things we need to know for binomials are in? What's in? Well, we select 5 dogs. So that's the selection. That's how many are in the sample, right? And then it wants to know, what are we interested in? How many are we interested in? That's our X value. And it says we're interested in none of them being golden, so the X value for this one is 0. So there's my binomial problem. It's a probability of 0 dogs out of 5, and we write it like that, probability of 0 for this one. Now, this is a straight binomial. You ask yourself, is this one in my table? Well, 0.5, definitely that's in your table, right? And sample size of 5, yep, that's within the range of our table. So go to your binomial table. There's no reason to do a calculation when you can just look this one up. And this will be on your test too. Your table will be there. So I'm going to go to an N of 5. And I'm going to go to probability of 0.5 on this first table. There's, I think I can get it all in there. There's my N of 5. My P of 0.5 is this column right here, and then I want the X value of 0, so it's the very first line, and I think I'm pointing to it, 0.0312. Is that what you're finding? I'm looking at it crooked, so that's the probability. That's all you had to do. So just look it up, okay? Questions? Are you with me? The probability of 0 is 0.0312, and we just did a table lookup for it. Okay, so next, what's the probability of a randomly selected dog being a golden if the probability is 0.32 and the probability of a female golden is 0.14? What's the probability of selecting a female given that the dog is a golden? Now, you got to recognize some things. When they say a female golden, they're saying female and golden, right? That's 2 different things we're looking at. So that's not a marginal probability. That's a combination, isn't it? So they gave me these things. Let me write down what they gave me. Probability of a randomly selected dog being a golden. So probability of just golden all by itself is equal to 0.32. Probability of female and golden. Okay, give me a minute. Write down female and golden while this thing's coming back on. Is 0.14, okay? So probability of just golden, 0.32, probability of female and golden, 0.14. Next, what do they say? They want the probability of selecting a female given that the dog is a golden. They want the probability of female given golden, right? Now, I don't really expect you to know that formula, but I do expect you to know how to find it, okay? So you go to your formula sheet and you say, okay, what I'm really looking for is a Chapter 3 problem, because this is not a binomial, is it? I'm looking for a Chapter 3 problem, and I'm looking for something that's going to help me if I have a conditional probability. I mean, I have a not a conditional, I have a joint probability given to me, and I have another probability, and they're asking for the given condition, the conditional probability. So look for your formula that says, you know, I'm looking for, a conditional probability, and here it is, right? Isn't this the one I'm looking for? This is a Bayes theorem. You see it? I want the conditional probability of A given B, and I already have the joint probability of A and B, and I have the singular probability, the marginal probability of just B. I have these two, so I can solve for this one. It's a Bayes theorem problem, and we should recognize that. So what is it? Well, it's the probability, and write it out for me. It's the probability of female and golden divided by the probability of golden, the given condition. That has to be the one that it's divided by, but that's Bayes' theorem. And you have female and golden 0.32, and you have just plain old gold, sorry, that's 0.14. And you have plain golden 0.32, right? So you can do this division. What do you get? Anybody? Go to 4 decimal places. What'd you get? How does that look to you? 0.4375? Do you understand it? It's Bayes' theorem. You can put out here if you want to, Bayes, so that you look for that formula. Make sure you know how to use it, okay? Now, we have a class success rate. Let's say if we have a class success rate of 79%, we randomly select 5 students from the class. What's the probability of, at most, 3 successful students? Well, now, this is another binomial, isn't it? They're either successful or they're not successful. So let's see if we can figure out the probabilities, what we need. We need P, and we need N, and we need X to do these binomials. Class success rate is 0.79, and they're asking about successful students. So that's my P. And then we said we selected 5. That's my N. And it said at most 3 successful. Well, now that's more than just one answer, isn't it? So at most 3 means it could be 0 or 1 or 2 or 3. Does that make sense to you? Okay, look at that probability, 0.79 with an N of 5. Is that in your table for table lookup? Is that in your binomial table? A P of 0.79. No. We have a P of 0.8, but we don't have a P of 0.79, do we? So we're going to have to do the formula, or we're going to have to use the calculator with it. For time's sake, I'm going to do the calculator, but you have this formula in your book, and you can just, well, you have to do some calculations with it, but you can figure it out, okay? The combination formula if you don't have the calculator. But I'm going to look these up. I'm going to say I want the probability of 0 or 1 or 2 or 3. That means I add them together, doesn't it? So do you remember how to get the binomial probability on your calculator? Let's see if I can turn this on. My battery's going dead. We're going to hope it lasts. I'm going to go to distribution right over this VARS. So I go second, and I have to scroll down for mine. And I come to A, which is binomial PDF. And I enter the number of trials. Well, the number of trials, I think it's 5, wasn't it? We selected 5. The probability of a success was 0.79. And I'm interested in, well, I'm going to start with 0. I got to look them all up, don't I? So I'm going to go 0 and paste it. Now that's what it looks like. Most of you don't have that little menu I have. So you would have binomial PDF, and it goes like this. It goes N, comma P, comma X. The only thing you're going to have a decimal in is that center one. Commas, no spaces, right? So when I hit enter here, I get this weird number. I get 4.08 to the negative e to the negative 4. So I got to move that decimal 4 places in a negative direction. In other words, I'm going to have 3 zeros in front of the 4. I usually only go to 4 decimal places with these, so the answer here is going to be for 0 is going to be 0.0004. No need to go any further than that. Let's do the second one. Now, there's a way to do this without having to go back through the function. Look up again. You can just highlight it. I just arrowed up until I got to it, and then I hit enter, and then I can go back and say, okay, I want to change that to a 1, and hit enter. And now this one is 0.0077, rounding to 4 decimal places, plus 0.0077. That's the 1. Let's do the same thing. I'm going to go up and highlight it and hit enter, and I'll go change the 1 to a 2 this time and just hit enter again. And it is 0.0578, right? Plus 0.0578. And now I'm going to do 3. Go up and highlight it, enter, change that 2 to a 3, and I get 0.2174. So now I need to add them all together. So I'm going to go 0.2174 plus 0.0578 plus 0.0077 plus 0.0004. I think I got those right. And I get 0.2833. So what's the probability that I choose 5 students? If we have a success rate of 79%, I choose 5 students from the class, and that at most 3 of those 5 are successful. Well, there's a 28% chance that at most 3 are successful. Okay? What's the next question they asked? Did I ask another one down there? Oh, I did this another way too. I looked up, to do this answer, I had to look up 4 different ones, right? I had to look up 0, 1, 2, 3. Okay, well, there's only 2 left, 4 and 5, in this whole probability distribution, because it only goes up to 4 and 5 to 5, right? I could have looked up 4 and 5, added them together, and subtracted it from the number 1, and I would have gotten the same number. Do you understand that? It would have been the other part, the part that I didn't use, the 4 and the 5. All of the probabilities for a probability distribution have to add up to a number 1. Don't use it unless you understand it. But if you do understand it, you can shortcut it. I could have looked up 2 of them instead of 4 of them. If you're doing those calculations by hand, that's a handy thing to know. Okay? All right, let's go to the next page then. Okay, so if 31% of all cars are white, what's the probability that now, I made up these numbers, okay? I mean, I made up these problems so that the statistics are not going to make sense. 31% of all cars are not white. So what's the probability that 4 or 6 cars randomly selected out of a group of 20 cars are white? Now look, the choices for this one is the car is either white or the car is not white, okay? It didn't say 30% or 31% are white and 40% are blue and 10%. It didn't say that. It just said 31% are white. The rest of them are not white. This is 2 choices. They're either white or they're not white. So this could be a binomial problem, right? It looks like a binomial to me. We're making a selection of 20 cars, and all the cars have the same probability. They're all independent. One car being white doesn't affect whether another car is white, does it? I mean, it really doesn't. So this is a binomial problem. I say P is white cars, right? 0.31. N is 20, because that's my group, and X is 4 or 6. Now, it didn't say 4 or 5 or 6. It just said 4 or 6. It can choose any numbers we want to when we're working with them. You've only got to do the calculation for the binomial twice and add them together, right? Because it's the same thing we were doing before. The probability of 4 or 6 is equal to, so you do the probability of 4, and then you do the probability of 6, and you find out. You go, however you want to do it, you go to your binomial PDF function, and you say, I've got 20 trials this time, and the probability of success is 0.31, and I want to know about 4 successful, 4 white cars. So when I hit enter on that one, I get 0.1181. Okay, so 4 is 0.1181. And I'm going to go back up here, highlight that one, and change it to 6. That's the only thing that really changes, isn't it? And it is 0.1907. So let's add those together. And you could just say, okay, I got 0.1907 or close to it. I could just add the other one, right? Go to 4 decimals. And it came out to be, I only need the first 4 decimals of it, 30.3088. Is that what you're getting? If you're using the formula, you're doing combinations and you're doing the probability of a p raised to the number of successes and q raised to the number of failures, which is, x minus n minus x. So a little more complicated, and that's why I don't think I have time to go through all of them, but if you need me to go through a formula after we finish this, I will. What's the probability that they are not white? Now that's not something you can just say, well, let's subtract it from 1, okay? The probability of not being white, if p is 0.31, q is the probability of not being white, isn't it? What's 1 minus 0.31? Well, 0.69. Wouldn't that add up to 1? Yeah, right? So now I've got a probability. I'm going to use a p this time of 0.69. Still, I've got an end of 20. And they're saying the same ones. They means 4 or 6, right? So the only thing I'm going to do is run it again with a different probability. I'm going to say 0.69 is now my probability, because that's the probability that they are not white. Wasn't it the opposite, right? So let's see if I can get back to this. Maybe I can just go up. Change my probability over here. Instead of 0.31, it's 0.69. And I'll run 4 first, just to keep myself straight. And I get a weird number. Okay, now look at this one. It's 7.9 exponent 6 places. I'm going to go way over here, and I'm going to push this exponent 6 places in the negative direction. In other words, I'm going to have 5 zeros in front of that 7. So the probability for this one of 4 or 6 is equal to 0.000, how many did I say? I'm going to have 5 of them, right? 4, 5, 7. Okay, that's the first significant. It really would be an 8 because I would have rounded to that one. All right, didn't I do that right? 5 zeros and an 8. Okay, so now let's see if I can run it the same one with a probability, looking for 6 of them. And this one's not too bad. I go and I'm going to have 3 zeros in front of the 3. So I'm going to say plus 0.0003, 1, 6, but that doesn't matter because I really just want those 2 together, okay? When I add 0.0003 to all of these zeros, it's just going to give me 0.0003. Don't even have to add that in my calculator. I can see it. So the probability of not white is not the 1 minus that you might think it is for this one. It's a different probability entirely, okay? Okay, let's go to the next one. This one is not a binomial, actually, isn't it? But it has a probability table given to us, and a probability distribution table of a discrete random variable. There are no ranges in here, and they want to know the probability of no more than 3. So write it down. It's the probability of what? Well, no more than 3 is 0. or 1 or 2 or 3. You just have to ask yourself, is this one included in no more than 3, okay? So when I ask myself that question, I say, okay, there's 0.04 is 0, plus 0.11 is 1, plus 0.18 is 2, plus 0.24 is 3, right? And I add those together. And I get 0.57. Okay, that's the probability of no more than 3. It included 3 and everything below that, didn't it? What's the probability of less than 5? Well, less than 5 includes 0. It includes 1. It includes 2. It includes 3. It includes 4. And it does not include 5, does it? Well, look, this is everything in the previous one plus 4, isn't it? Isn't that going to be equal to, this is 0 through 3. If I add 4 to it, that's really all I have to do, because I've already done 0 through 3. This one is 0 through 4. And as I do that, I find it is 0.71. You good with that? Now, probability of at least 4. What you got to do is figure out what's included in at least 4. Well, is 4 in there? Yeah, and everything bigger than 4, right? So you can add those 4 together, or you can look at it this way. Look, guys, I already figured out 0 through 3, didn't I? You see this one? 0 through 3 is 0.57. 4, 5, 6, and 7 would be 1 minus 0.57. I'm telling you the shortcut because it's obvious how to do it without it. You just add them 4 of them up, right? You should get the same thing if you say 1 minus 0.57. I don't think I did it this way, so let me just double check this and see what I've got. I get 0.43, and that's what I got when I added the 4 of them together. Did you understand it? You understand what I'm doing? Yeah? Okay. Okay, so now what's the mean? This is not a binomial, is it? So how am I going to get the mean if this is not a binomial experiment? Well, the best way is to put the x values, this is discrete random variables, put these in list 1 and put these in list 2 and then run one variable statistics on it. So let's kind of do that and see what happens. I'm going to go stat and edit, and I'm going to go clear some lists here, list 2 and clear list 1. And then I'm going to write the list 1 variables 0, 1, 2, 3, 4, 5, 6, 7. And check, see if I did it right. And then come over here and put their probabilities in. 0.04, 0.11, 0.18, 0.24, 0.14, 0.17, 0.09, 0.03. I think I got those entered correctly. After you enter it, it's stat, and you go to calc, and one variable statistics. List 1, use frequency list is list 2, so it's L1, comma L2. What's the mean? Well, 3.35. And it only gives you one standard deviation, 1 point, and we'll go to 4 decimal places with those, 1.7226. Okay? Did you get the handout? Okay? All right, so next, I've got a contingency table missing the totals, right? So I don't even get started until I add these things up. So I'm going to add male and female here, and I get 390. I'm going to add these, male, female, and I get 540. I'm going to add these male, female, no opinions, and I get 70. And then when I go out to the totals, I add all the males here together, and I get 624. I add all these females, the female row together, and I get 376. And then I check myself. I add all three of these totals and these two totals together, and it's all 1,000. Okay? There's your totals. I know you are capable of doing that, so that saves us a little time. Now, see how many of these questions we can answer from the contingency table. What's the probability of Republican? Well, they're asking just the probability of Republican all by itself, nothing else with it. It's just two numbers, total Republicans over the total. Probabilities are not listed in percentages unless they ask you for them. So listed as a decimal, right? Divide by 1,000, you just move the decimal place 3 places to the left and you're done. Okay? What's the probability of female? Total females, well, that's 376 over the total. These are marginals. They're only asking about one thing. All the answers will be found up in these totals, the blue numbers I've written in, right? Divide by 1,000, I get 0.376. What's the probability of male or no opinion? That's different, isn't it? Probability, I'll write it like this, probability of male or no opinion. I have to ask myself, do I have any that are male and no opinion? Are any of those males no opinion? How many? 28, right? These are no opinion males, right? So I have to add all the males, all the no opinions, and subtract out the ones that are both. Remember this one? We go fractions, don't we? One fraction plus another fraction minus the third fraction. All of them have the total as the denominator. So that makes it easy. It's the way we always start. And now I'm going to say, how many males? Okay, total, 624. How many no opinions? Total, 70. And how many are both? These 28 got added in that total and this total, didn't they? So I'll subtract those. So I really just say 624 plus 70 minus 28 is 666 over 1,000. And then I do the division. I get 0.666. Okay, probability of female given. This is a given condition, right? Probability of female given Democrat. This time, you are only going to look at the given condition, that Democrat, right? So the only part of my table that I'm going to use is right here because it is a given condition. Rest of the table can just disappear. So then I look at my question again. Probability of female inside there is 184 over what total? Well, the only total that I'm allowed to look at is inside the Democrats. So I do 184 divided by 540, and I come up with 0.3407, right? Probability of male and Republican. Now, that usually means multiply, doesn't it? But then I have to say, are they dependent or independent, right? Now, except I have a table. I'm sorry, I've kind of lost track of where I was. If I have a table, it doesn't matter if they're independent or dependent because table lookup is the same shortcut for both, right? So male and Republican, I just look at how many are males and Republicans right here, 240. And I put that over the total, and I get 0.24. Shortcut works whether they're dependent or independent if you have the contingency table. Now, the last two questions are about mutually exclusive or not. Are Republican and no opinion mutually exclusive? Yes or no? What do you say? Somebody tell me. This is not a mathematical check. This is a common sense check. Can somebody have answered the survey that they were both Republican and no opinion? No. Then they are mutually exclusive. What about male and Democrat? Can somebody have answered the survey that they were both male and Democrat? Yes. So are they mutually exclusive? No, they're not. Okay? Any questions on that page? Because I tried to put a lot of questions about a contingency table on that one page. So most of your contingency table type of questions are here, okay? What you can do with them. Joint probability, conditional probability, right? You've got the union probability, and you've got mutually exclusive questions. It's all here. And just marginal probability also. All right, so next, if 40% of all Americans love blue, what's the probability that 4 out of 10 people asked love blue? Okay, so the responses here, as far as we're concerned, are they either love blue or they don't love blue, okay? It didn't go into how many really love red. It just said they love blue or they don't love blue. We have selected 10 people, and we're asking about 4 of them. And is the probability that all of these people love blue, would it be independent? I mean, would the fact that one of you loves blue affect whether the other one loved blue? Okay, so they're independent. This meets all of the conditions for a binomial, doesn't it? So if we have a binomial, that's the way we do it. We say P is the probability of loving blue. Well, that's 0.4. We say N is how many we are selecting or sampling. Well, we ask 10 people. And we say X is the number that we're interested in loving blue. Well, that's probability of 4. Okay? Can you use your binomial table to look this one up? Yes. So use your binomial table and look it up. Go to your book, find your binomial table, and look this one up. Okay, what do you get? Is this what you're finding? 0.2508? Check it, because I was doing this while I was watching the Super Bowl last night. I can have made a bunch of mistakes. Are you good? Binomial table lookup, use it if you can. It's so simple. All right, now let's talk about possible outcomes. Now look at the wording, because this is not the same as how many different ways can something happen, okay? Or how many different selections can be made. This is the total possible outcomes. Do you have, if you take a 6-sided die and you roll it 5 times, well, think about it in stages. The first trial or the first stage, you have 6 possibilities, right? That's the first roll. The second time I roll it, how many possibilities do I have? It's still a 6-sided die, guys. How many possibilities do you have? 6. The third, the fourth, the fifth. Really, that's it. Each time I roll it, I've got the same number of possibilities. I just multiply them together to see how many possible outcomes I have, okay? Okay, and that came out to be 6 to the power of 5 if you want to do it as an exponent, right? and I got 7776. Okay? All right, let's look at snowboarders. I was thinking Olympics when I wrote this one. So we have 8 snowboarders. How many different ways can the first, second, and third places be awarded? What kind of question am I asking you? Anybody? What have you got? You've got the types of questions we've got: total possible outcomes, permutations, combinations. Which one is this? It's close. It's asking about order, so it changes it. It is a permutation. Okay? So out of 8, we're saying how many ways can the first 3 be ordered? Okay? And you take your calculator and you run a permutation, right? I don't know if you remember where it is or not, but it is under math, probabilities, and it's a permutation, the P. For mine, I say 8, and then I go over and enter a 3. But for you, you may have to enter the 8, go find the permutation button, and then enter the 3. See if you come up with this, though. 336. Okay, next question. The probability of a child loving candy is 0.79. If we randomly select 2 children, what's the probability that the first loves candy and the second does not? Are these independent of each other? Are these independent events? Does the first child loving candy affect whether the second child loves candy or not? Common sense will tell you that your preferences don't affect the person sitting next to you, right? Okay, so these are independent. So if we have the probability of the first and the second loving candy, right? And we have 2 independent events, all we do is multiply their probabilities together, isn't it? Okay, so this one is the probability of yes and no, isn't it? What's the probability of yes? Well, the probability this child loves candy is 0.7.